In this problem, we are observing a situation where we can calculate the mass from the vibrations of a given machine. So here we can see a method in which astronauts can measure their body weight without having the assistance of gravity, such as we do in conventional scales. So when we have astronauts spending a long time in orbit, they need to measure their body mass as part of their health maintenance programs. On Earth, it's simple. We just stand on a scale and see the mass, where the magnitude of the weight is divided by gravity and the mass is displayed on the scale. But this doesn't work in orbit because the scale and the astronaut are not, they are in a free fall and cannot press against each other. So the astronauts use instead a body mass measurement device shown in this figure here. It's made of a spring-mounted chair in which the astronaut sits. The chair starts oscillating in simple harmonic motion, and we measure the period. And then this is converted to get the mass. How do we do this? We know that for simple harmonic motion, the angular frequency is radical k over m, and the angular frequency is 2 pi over t. So if we have k and we have the mass, now the mass here is going to include both the astronaut and the chair, and we have k, then we can find the mass from the measured value of the period of oscillation. So they told us that in this example, we have a spring of constant 606 newtons per meter. The mass of the chair is 12 kilograms, and the period was found to be 2.41 seconds. And we want to find the mass of the astronaut. Of course, we just substitute all the values we have here. So this is 2 pi over, first of all, let's just rephrase the formula for the mass. So if we rearrange this formula, 2 pi over t squared will be k over m. So m will be k t squared over 4 pi squared. And this mass, of course, is the total mass. So it will include the mass of the astronaut plus the mass of the chair. So if I want to just write a final formula for the mass of the astronaut, this is what we will get. Okay, so now we just have to substitute everything. K is 606, T is 2.41, this is squared, over 4 pi squared, minus the mass of the chair, which is 12. And if we solve this, we will get 77.2 kilograms. This is the mass of the astronaut as measured by this chair.